the title of this talk is about the thermodynamics of black holes. Well, you know, I think that most of you have attended the general relativity course or lecture, which was offered this summer. And if you have done it, then you know that in general, in general relativity, then black holes are some solutions of the Einstein equations, but they are not thermodynamic objects. I mean, they don't have a temperature, they don't have an entropy. They are just some mathematical solutions. Yeah, and this is because the theory is classical. I mean, general relativity is a purely classical theory. Yeah. So on the other hand, as soon as you try to put some quantum mechanics in the game, then it turns out that these black holes have actually a temperature, an entropy, sometimes also pressure, and so on. Yeah. So these are purely quantum mechanical effects. Yeah. And this was discovered for the first time by, as maybe you already know, by Hawking, Bekenstein. Yeah. And so the goal of this lecture, I mean, this is a pedagogical lecture, which is intended for students who still haven't seen these things. Yeah. So the goal of this lecture is to derive these properties of black holes. So how can you derive the temperature, or how can you derive the entropy of them, and so on. Yeah, and we do this by, I mean, there are several ways in which you can do that, and the way we do today is using the path integral formalism. Yeah, so that's the reason why we will first recall some basics of the path integral formalism, which we will later apply to gravity, to black holes. Yeah, so let me write it here. I think now we have the first part, which is yeah. So it will just a reminder. Maybe you already know most of that about the path integral formalism. Yeah, because this the formalism that we will need to derive the thermodynamics properties of black holes. Yeah. In particular, we have a subsection which is a reminder about the propagator in quantum mechanics. Yeah. So if you remember the basics of quantum mechanics is the Schrödinger equation. Yeah. So which is IH bar, then derivative of psi with respect to time equal to h, where h is Hamiltonian times psi. So here I will just number the equation in case I will need to refer to them later. Yeah. So this is the general expression of the Schrödinger equation, and the solution can be written this way. So the ket psi or psi is then equal to the action of some unitary operator acting on the state at time t0, where this u is, as I said, as a unitary operator, which depends on two instants of time, so t and t0, and it's just an exponential, so it's just the exponential of the Hamiltonian, so minus IH bar t minus t0 h. Yeah, so this is also called the evolution operator. And it satisfies some properties like the composition property, namely you can write u, I mean, if you multiply it twice, so if you multiply u of t1, t2 times u of t2 and t3, then what you get is just u of t1 and t3. Yeah. And now if you have a wave function at some initial instant of time, Then you can express the wave function at another instant of time in terms of the matrix element of this unitary operator. So let's say that we have a wave function psi, which depend on q, where q is just a generalized coordinate. It can be either one coordinate if you are in one dimension, or it can be more than one if you are in more than one dimensions. Yeah. So let's suppose that we have now a wave function that's at time t0, and then the idea is that we can now express the wave function at time t in terms of the previous wave function. So we can express psi of t for t greater than t0 in the following way. So psi of q and t. Well, what is a wave function is just the the coefficient of the expansion of the state in terms of the eigenstates of the position operator. So this just the scalar product between q and psi. So this can also be expressed as q, and then the action of the unitary operator acting on psi. So this is u of t t0 acting on psi of t0. Now there is a trick that we can do, namely we can insert the identity operator. And the identity is, if you remember, there is this, you can write the identity in the following way. Yeah, if you remember. Yeah, now we are going to insert this expression here. So in the previous equation. So we have q of t t0, and then the integral over q0, q0, q0. So this is my identity times psi of t0. Yeah, and now I define this quantity. So the quantity that I have here as the propagator. So this is my definition of propagator. So this is my integral over q0 of some k of q0 t t0 times psi. Yeah, so this is my so this is called the propagator. And from comparing both sides, you see that the propagator is just the matrix element of the u operator. So it's just q0 t0 equals to q, u, and q0. Yeah, so this how you so this is where the notion of propagator comes from. Yeah, so so we started from here. We want the wave function at some time t. Yeah, and the and you obtain it as soon as you integrate the previous wave function. So the wave function that you have at time t0 times this new object, which is called the propagator. Yeah, and the propagator, as you see from the definition, is nothing but the matrix element, indeed, of the unitary operator. Yeah. So this propagator gives the quantum mechanical amplitude for the transition between an initial state q0 at time t0 to a final state q at time t. Yeah. Okay, so this is the definition of the propagator, and which is a formal definition because I didn't specify some. I mean, it's just the normal definition, but there is a way to express it in a better way using the path integral formalism. Yeah, so that's the reason why now we see how to express the propagator as a path integral. So first of all, a path integral is just an integral over some trajectories, so which we are going to see again better. So the propagator itself can be expressed as an integral over all trajectories connecting the initial and the final states. Yeah. So let's compute it. And for simplicity, we just stick to a system with a 1 degree of freedom. Yeah. And so we are on a line. So we are in 1 dimension. Yeah. And okay, suppose this is our time interval. Yeah. So this is our time. And what we are going to do now, we divide the interval which goes from t0 to a final tf into very small intervals. Yeah, so this would be the interval t0 t1, then from t1 to t2, and so on until you get tn. Yeah, so we have in total n plus 1 intervals. And at the end, we will take the limit for n going to infinity. So at the end, we want to recover the continuous limit. Yeah. So for now, we have discrete system where we have some finite number of intervals, but then at the end, we will take the limit for n going to infinity, because we want to recover the fact that time is a continuous, at least here, as far as we know. So now the idea is to compute the unitary operator. Yeah, and if you remember, there is this composition, a property of the unitary operator that I have written here, namely this one. Yeah, and now we are going to use that. We apply n plus 1 times this composition property each time for each interval. Yeah, so we were here. So we do a composition. So we now write u, the evolution operator, which goes from t0 to tf. Now is going to be a product of unitary operators. So the operator from tn to tf up to the operator from t0 to t1. Yeah, so this is just a product from 0 over k from 0 to n of u of tk plus 1 tk. Yeah, with also the identification tf is equal to tn plus 1 and ti is equal to t0. Yeah, so tf is the final time is equals to tn plus 1. Ti is the initial time, is just my t0. Yeah. So now we can compute k, so our propagator. So k, which remember is a function of q0 qf, t0 tf. According to the definition, it's just the matrix element of u. So just qf, u, and q0. Yeah, but u is just a product, so I can write this as a product of k from 0 to n of tk plus 1, tk, and q0. Yeah. So this is our starting point. Now we are going to insert the identity using the property of the identity written as an integral. So this identity, so I equals to the cat q bra q, cat q bra q. Yeah, we are going to insert this n times. Yeah. So now we have from here, we have qf, then u of tn plus 1 tn, and then we have the identity. So integral over qn of qn, and then u of tn, tn minus 1. And then we do of k plus 1, q k plus 1 times u, and so on and so forth, and up to the last one, which is the integral over q1 of q1, q1, and then u. Yeah, so q0, q1, q2, and so on, they label the different quantum states at the instance t0, t1, t2, respectively. Yeah, so we have this series of terms, and thus we see that k, our propagator, is just then the integral over qn, qn minus 1, q, and so on up to q1 of the following things. So of the product from k0 to n of the propagator for each small interval. So q of k1, qk, tk plus 1, tk. Yeah. So the total propagator is just the product of the propagators for each interval. Yeah, and then at the end, then of course we are integrating here. We are integrating over all the coordinates over q1, q2, and so on. So this was equation 6. Yeah. So now we have to compute this object. So the propagator for the small interval. So for each small interval. Yeah. So we need this propagator. Yeah, so the propagator, so the matrix element of u of k1, tk1, tk. Yeah, so we want that. So in order to do that, in order to compute that, let's just focus on the u operator here. The idea is to expand the evolution operator, do a Taylor expansion of the operator. Yeah. So let's do a Taylor expansion. So u. So let's do an expansion. U is then, if you remember from the definition, it's just an exponential. So it's now easy to take some the Taylor expansion of that. And why are we allowed to do such an expansion? Well, because you have here inside the delta tk, which is the width of a single interval. But since at the end we are going to take the limit for n going to infinity, then each interval has a very, very, very small length. Yeah. So delta tk is very, very small. So we are allowed now to do a Taylor expansion up to first order. Yeah. So we can write 1 minus I delta tk h, and then of course we would have the terms squared. So delta tk squared, but this is even smaller, right? Because delta k is small, so delta tk squared is even smaller. So we can neglect that. Yeah. So only the first term, so at linear order, or at first order, we just need that. Yeah. So it means that k. So the things that we have, this one. So let me copy this. Yeah. So our k here is then equal to q of k1, and then the expansion here inside, delta tk h qk, plus other terms of order delta k squared. Yeah. So far so good. We just did very logical steps. So now how do we proceed from here? Well, here you see that this is a matrix element of the Hamiltonian. You see you have on the left eigenstate of the position operator, then you have the Hamiltonian, then on the right another eigenstate of the position operator. Yeah. So we just need this object, Q of K1, H, Q of K. Yeah. So in order to do this, I can use the trick of writing the identity in terms of an integral over, in this case, over the momentum. And why did I do this? Well, because now you see that we have something which you know, because you have here the metric cell, so the scalar product between an eigenstate of momentum operator, so pk here on the right, and then an eigenstate of the position operator on the left, so qk plus 1. Yeah, and this the expression of that is known from the normal usual quantum mechanics. Is just the so this is equal to this normalization and then the exponential of the product momentum times space. Yeah, so this is the usual result that you know from quantum mechanics. Yeah. Okay, so now we what we can do is we can always if I have an expression which contains momenta and position operators, I can always move the momentum operators to the left. So I can always put the P operators to the left. So I can always write the Hamiltonian in this form. So I can write it as some sum of terms of some function of P on the left, and then some function of Q on the right. Yeah, so this is a so-called normal ordering where you choose an order for the operator. Yeah, of course, when you do this, then one has to take into account the commutation relations, but at the end you are always able to put the P operators to the left. Yeah, and why we do this? Well, because as a result, it turns out that the matrix element of H between P and Q then becomes well, the Hamiltonian itself. So Fjpk G of Qk times Pq Qk. Yeah. So since now the Hamiltonian contains the momentum on the left and the position on the right, then you can act on then it's easy to act on the corresponding eigenstates. Yeah. On the right, I act with the position operator on the eigenstate of the position operator. On the left, I have the momentum operator, and then I can act easily with the position operator. Yeah. So that's the reason why now these are the so these are not operators anymore, but they are the eigenvalues, the result of the action of the Hamiltonian on the eigenstates. So you find something like now H, some function of P and Q times Pk Qk. Yeah. So this then is also equal to, because of the result of before, then it's just H Pk Qk times the exponential of minus I Pk Qk divided by H bar. Yeah. So now if we combine 9 and equation 9 and equation 10, then we arrive at Q of k plus 1 H Qk. We have a single integral over the momentum. This function is just a function of Pk of the momentum and the position times the exponential of I Pk times Qk plus 1 minus Qk divided by H bar. Yeah. So these are the matrix element of H between the momentum and the position. So now that we have this, we can go back to equation 8 and get the what we wanted. So we wanted the propagator for a generic small interval. So we wanted k of qk plus 1, qk, tk plus 1, tk. Yeah, so we want that. So if we now insert everything there, then we have the integral over pk divided by 2 pi h bar, and then the exponential of I delta tk divided by h bar, qk, pk, and then qk plus 1 minus qk divided by delta k minus h. Yeah, then in principle, some terms proportional to delta k squared. Yeah, so this the generic propagator for a single interval. And then if you remember, the whole propagator is just the product of that. So here we have qf q0 and then tf t0. That is just the product of terms, so a product of k from 1 to n of dpk dq k divided by 2 pi h bar dp0 2 pi h bar times the exponential of the previous quantity. So we have an exponential of a product of exponentials, mean that you have an exponential, you have in the exponent a sum of terms. So we have a sum of I delta tk divided by h bar, and then pk times qk plus 1 minus qk divided by delta tk minus h plus O of delta tk squared. Yeah, so this the propagator, the final, well, not yet the very final, but still we are almost there. This is the propagator that we have for that interval. But as you can see, this is just this is still a discrete expression. It's discrete because we still haven't taken the limit for n going to plus infinity. Yeah, you see, we still have the product from 1 to n. Then we have the sum from 0 to n. Yeah, so the last step is then to take the limits for n going to infinity. So you increase the number of intervals, which means that now the length goes to 0. The length of the interval then goes to 0. Yeah. So it means that if you take the limit of what you had before, what we have before, then the sum becomes an integral. So this quantity here, now becomes an integral. And this delta tk now becomes the measure of the interval, becomes a delta t. Yeah, so now the final result of this limit would be then that we get an integral from t0 to tf over t. So this is a delta t, and then p of t times the derivative of q with respect to time minus h, which is a function of p and q. Yeah. And why do I have here this? So this is the derivative of q with respect to time. Well, it comes from here. Yeah, this is nothing but the discrete form of a derivative. Yeah, this is just the definition of the derivative. So as soon as you take delta t to 0, this is just the definition of the derivative of q. Yeah, so that's the reason why here we have delta qt, derivative of qt with respect to t. Yeah, and now everything now is a function of t. So p is a function of t, q is a function of t. Yeah, where t is time. Yeah. So we can introduce, last but not least, we can introduce this notation. So delta p, delta q, I define it to be the measure of my path integral, and I define to be the limit that you have inside. So the limit of pk qk times dp0. So if I now if I now say that this limit, which is infinite because it's an infinite product of terms, if I say that this now is the measure, if a measure of an integral, then I can rewrite equation 13 in the following way. So I can write the path integral. So I can rewrite the propagator in the following way. So as an integral over p and q, and then an exponential. So I divided by h bar, integral from t0 to tf, p q dot minus h delta t. Now here we integrate with some boundary conditions. So q at the time t0 is q0, and q at the time tf is qf. So this is equation 16. So this is my final result. Yeah. So here I just use equation 13 of before, namely, yeah, this one. Yeah. Using this identification, so using this measure. Yeah. So you can see now we have the propagator k written as an integral. This is a functional integral. This is not a normal integral of calculus, because here we are integrating over a function itself, so not on variables like x, y, but rather of a function of t. Yeah, so this is why you call it a path integral, because you are integrating over different paths in phase space, right? Because you are integrating over all possible p, momenta, and q positions. Yeah. So this is the path integral formula for the propagator. Yeah. And of course, here we derive that for a very simple system. So if you're for a one-dimensional system, but of course you can replicate the calculation, you can generalize it for any type of dimension. So for n dimensions, for example, or also for an infinite number of dimensions if you are dealing with fields. Yeah. And yeah, okay, so let me see what I can say about that. Yeah, okay, so I think we can specialize a little bit to systems with finite temperature. Yeah. So we are going to use this. We are going to use later this formula. Let's see how we can generalize this for fields. So as you know, a field is just if usually you are used to have particles where you can count them. You can say, okay, this 1, this 2, this 3, this n, and then for each of them you can assign a trajectory. So q1 of t, q2 of t, and then qn of t, and so on. But then there are also other things which are fields, like phi of x. And in this case, you have it's like having an infinite number and continuous number of coordinates q. Yeah, because at every point in space you can associate a number. Yeah, so x is a real number, so you have an infinite number of points, and to each of these x you have some value phi. Yeah, and yeah, so x is our new label, so it's not 1, 2, 3, n anymore, but just a continuous label. Yeah. So let's see how can we deal with path integrals and propagators also for fields. Yeah. So as we have seen in the previous section, so let me write it here again. The propagator can be written in the following way. So it's well, first you have the definition. And then we have the result of before. So you can write it as a path integral. Delta Q e to the I s divided by e to the I s divided by h bar. Yeah. Okay. So in here in the previous result, I had also an integration over the momentum. But the idea is that if the Hamiltonian is quadratic, it's a quadratic function of the momentum, then the path integral can be simplified, and you get only this expression here. Yeah. So maybe I write it here. So if the Hamiltonian is a quadratic function of the momentum, then the path integral is simplified as in this way. Yeah. So here I think I will not have time to derive also that, but you can look it up. I can give you some books later. Yeah. The idea is that if the Hamiltonian is quadratic in the momentum, so it's like if it is like p squared divided by 2m, as usual for the free particle, for example, then the path integral can be simplified in the following way. So it's just an integral over q and not over p. And then you have in the exponential, you have s, where s is the action. So the action for the classical theory. Yeah. So this the form of the propagator that everyone uses, because usually the Hamiltonian is always quadratic in the momentum. So usually you can always recast that general expression of the propagator that I have written here. You can always recast into this form. Yeah. So this is the form that you don't have to forget. So this is delta q e to the I s divided by h bar. Yeah. So this is a starting point for everything. Yeah. Now, if you have a theory of quantum fields, so you have a quantum field theory. You can generalize this formula very easily. So in a quantum field theory, you would compute. So the states now are fields. So you compute this type of transition amplitudes. So now the generalization is you integrate over phi. So you don't integrate over q, you integrate over phi. So the generalization is very easy. With always the boundary conditions, phi of ti is equal to phi I, and phi of tf is equal to phi f. Yeah. So this is so this was my equation. So the 16, I think 17, and then this 18. Yeah. So this is the form of a generic, transition amplitude or propagator, as you want, computed in terms of a path integral. Yeah. So the recipe is very easy. So you just apparently easy because it's just the exponential of the action. So as soon as you have the action, then you just exponentiate it, and then you integrate over phi. Of course, this in practice is difficult because, because you have to integrate over phi, and the phi dependence can be very complicated. So usually only for very specific systems, you are able to compute explicitly the propagator. So for something like the free particle or the harmonic oscillator and so on. Yeah, and we will see later that we can compute explicitly for black holes. So we will use that to extrapolate some thermodynamic properties of black holes. Yeah. Now, in quantum mechanics, there is also the notion of partition function. So for a system with Hamiltonian H at a temperature T, so for a system with Hamiltonian H at temperature a temperature T, which I also write as b to the minus 1. Then the partition function is usually defined as the trace of the exponential. Yeah, so it's a trace means it's a sum of all the diagonal entries. So this is equations 19. Yeah, where these n they form a basis of the Hilbert space. Yeah. Now, if you are in a quantum field theory, then states are represented by field configurations. So the generalization for fields is the following. So Z is then now not a sum anymore, but a continuous sum, so an integral of phi e phi. Yeah. So now, if you perform so-called weak rotations, so if you just say that the time is minus I tau, so you just say your time t is equal to minus I tau, where tau is also called the Euclidean time, then a generic amplitude becomes something like that. So you so final initial e tau I phi I. Then this just becomes an integral of some measure, which is not necessarily the previous one because we did a weak rotation. And then e to the minus s, where s is the Euclidean action, so the action where you have done this transformation. Fx phi f. Yeah, so this is 21. Yeah. So now if we make the identification, beta equal tau f minus tau I, which means that if time is periodic, then we can use 28. So we can use 21 to compute 20. Yeah, so we can use this, so the last one that I have written, to compute that. Yeah, indeed, I could write the following. I could write z. So z is the integral over phi, then the integral over phi, the tilde phi of e to the minus se of phi. And this is also an integral over phi where you have periodicity of e to the minus se phi. Yeah, well, so it means that the path integral is restricted to those configurations which satisfy the periodicity condition phi of tau equal to phi of tau plus beta x. Yeah, so as soon as I do this identification, so if I say that time is periodic with period beta, where beta is the inverse temperature, then I can compute then these two formula 20 and 21 are the same. So it means that I can compute a generic transition amplitude, or I can compute the partition function using the path integral formally. So I can, this my left hand side is my right hand side. Yeah, so I can compute a generic partition function using this path integral. Yeah, and this can be done in every quantum field theory system which has a temperature. Yeah, so this is the lesson that we learn. So in order to put a theory at finite temperature T, one has to compactify the time direction on a circle of radius beta, where beta is the inverse temperature. One has to compactify time, so the time direction, on a circle on a circle of radius beta, where beta is 1 divided by t. Yeah, and also on the other hand, you can say that if you have a system where time is periodic, then the system has a finite temperature. Yeah, so you can go in both directions. Yeah, so why is this important for us? Well, because we want now to derive the temperature for a very particular system. So for I want now a quantum field theory which lived on the background of a black hole. I want now to put a periodic time, and then from there I want to compute the temperature of that. Yeah, so this will allow us to compute the temperature of some of these systems. So for a black hole. Yeah. So the first thing to do will be then to compute the partition function of that. So this is this is the lesson that we to learn. Yeah. So let me say it again. So in order to put a theory at finite temperature, then one has to compactify the time direction on a circle of radius beta, where beta is the inverse temperature. Yeah. So now let's use this very important thing in order to compute the Hawking temperature, so the temperature of a black hole. And then we will do the same for the entropy. So usually I use black, so blue. So okay, Hawking was the first person to derive to discover or to argue that black holes have a temperature, but he did it in another way. He used the Bogoliubov transformations. So today we are doing that with the path integral formalism. Yeah. So let's suppose that we want the partition function for gravity at certain temperature. Yeah. So suppose that we have a certain theory of gravity, and this theory has a certain temperature. So it's not at 0 temperature, which is forbidden by the second law of thermodynamics. Yeah, but it has some temperature. It can be as low as you want, but it is not 0. Yeah? So we want now the partition function. Partition function for gravity at temperature T. Yeah. So according to the receipt, then the partition function can be written as a path integral, where you integrate over all possible fields. Here, the field is just a metric G, so I integrate over the metric. Yeah, so this is also equation 23. Yeah, so I suppose that I only have gravity in my theory for now. I don't have any matter fields up to now. So it means that the partition function is just an integral over the metric itself. Yeah, and S is the action of this theory. Remember that S is the action of the class of a classical theory. Yeah, so the path integral formalism is the, if you remember what I said before, is just this integral where you integrate e to the is, where S is the classical action, so the action for the classical theory. Yeah, so path integral means that a sum of classical things gives you a quantum object. Yeah, so sum of classical is equal to quantum. Yeah, here I am summing, so integrating classical things, so like the action on the right hand side, and then on the left hand side I will have a quantum object, so a partition function, or some amplitude, some transition amplitude, and so on. So now S has to be the classical action. So what is the classical theory of gravity that we have? Well, the Einstein theory of gravity, so GR. So S is then the Einstein-Hilbert action. The action in Euclidean signature. Yeah. And now there is a tricky part, because we do not need only the Einstein-Hilbert action, but we also need a boundary term. Yeah, so because here we are integrating on some manifold, and it's possible that for this manifold to have a boundary. Yeah, so S will be the Einstein-Hilbert action plus some boundary term. And this boundary term is known as the Gibbons-Hawking term. Yeah, so S is then equal to the usual Einstein-Hilbert action. Here I integrate over some manifold M. Let's do the calculation in the general. You have d dimensions, so this is a ddx square root of gr, and then we have the expression of the Gibbons-Hawking term, which is a boundary term, which is this integral, where gamma is the induced metric on the boundary. On the boundary, which is delta m, and k. So k is the so-called the trace of the extrinsic curvature. So it's defined in the following way. So it's just a contraction of gamma mu nu, so of the induced metric, with the covariant derivative of n nu, where n is the outward pointing unit vector normal to the boundary. So these additional terms, this additional term, which is the Gibbons-Hawking term, is there to guarantee a well-defined rational principle. Yeah. So usually if you have a sphere, for example, then you don't have a boundary, so you don't need to put it. But in general, if you have a manifold with a boundary, then you have to insert that. Yeah. And so we now take the black hole geometry as the background for some field theory at finite temperature. Yeah. So I want to have I have my black hole geometry, which is described by some metric, which is some function f times delta t squared plus 1 divided by g dr square. So you can think of it as the Schwarzschild solution, for example. This in the usual metric in d dimensions. Yeah, so we have a spherically symmetric metric, and is the background for the black hole. And now in this background, so this is a curved space-time. So don't forget, this is not flat, this is curved. This is a curved background. And now in this background, I assume that there is a field theory, there is a quantum field theory at finite temperature. So this is the background for a field theory at finite temperature. Yeah, so I assume that somehow somehow I could describe the black hole by studying this theory instead. Yeah, so I have this field theory which lives in this background, and this field theory is a finite temperature. So it's not at zero temperature, but it has some not zero, maybe small, but not equal to zero temperature. Yeah, and according to what we have seen before, that it means that the time direction has to move on a circle, has to be compactified on a circle. Yeah. So I think now we have 1 hour, so maybe we can do a break here if you want. Yeah, And then we continue with these calculations, which is very interesting after the break. So if someone has questions, can ask here. Otherwise, let's just some small break.
Yes, please feel free to unmute yourself or send questions through text.
Okay, then if no one has, then see you later.
We'll be back in 10 minutes.
Yeah, okay, yeah. Before the break, we were saying that, so we have this curved spacetime, which is the black hole spacetime, which is curved. Then there, I assume that there is some quantum field theory at finite temperature. Yeah. So the theory there has some temperature, and then after some time, it will come to a thermal equilibrium with the black hole. So if I find the temperature of the field theory, then I have also found the temperature of the black hole. So this is the idea. And we don't care about the details of this field theory, just a generic one. It could be some theory of scalar field or whatever. Yeah. So the important here is that we assume that this field theory has a finite temperature, and then it goes in thermal equilibrium with the temperature of the black hole, such that if I find the temperature of the field theory, then I know also the temperature of the black hole. Yeah. So we also assume that that both F and G have a first order zero at some point. So have a first order zero at the position of the horizon. So the function F vanishes when it is evaluated at RH, but the first derivative does not vanish. And similarly for G. Yeah. So this is the case also. This is the case for Schwarzschild metric, for example. Now, if you are close to the horizon, then we can expand. We can do a Taylor expansion of the functions. So close to the horizon, then we can say that f of r is approximately equal to f prime times r minus rh plus r minus rh squared. And the same goes for g. So g will be approximately equal to g prime times r minus rh plus r minus rh squared. Now let's insert this expansion into the background. So into this into 25. So now we obtain ds squared, then will be equal to f prime of rh times r minus rh d tau squared plus 1 divided by g prime. And then dr h squared plus the angular part of that. So this is equation 26. So now let's define let's do a change of coordinates. So I could define the following quantity. So rho squared, I define it as 4 r minus rh divided by g prime. And then I define this phi as 1/2 times the square root of g prime times f prime times tau. Now, if you do this, if we make this change of coordinates or change of variables, then the metric changes accordingly in the following way. Then ds squared is equal to rho squared times d phi squared plus d rho squared. Yeah, so you see, you've plus, of course, the other terms. And this expression of the metric is famous because it's just polar coordinates. Yeah. So rho and phi can be interpreted then as polar coordinates. As polar coordinates. So it means that phi is then an angle, and phi is an angle is periodic. The polar angle is periodic with period 2 pi. So phi is periodic. However, phi was proportional to tau. So it means that tau is then also periodic with this period. Yeah. And so we have obtained the following. So we have obtained the fact that this time, this tau, so time tau is periodic. Yeah. So now if so if you remember, then to when you have a theory at finite temperature, the time is periodic, in fact, with the period which is given by the inverse temperature. Yeah. So we have found something very beautiful. We have found that time is periodic. And now if we identify these things with the inverse temperature, then we are done. So the period, so we know that we have a theory at finite temperature, so the period must be the inverse temperature. So 1 divided by t, or I can immediately invert. So t is then equal to the square root of f prime r times g prime divided by 4 pi. So this was equation 29. So we have obtained an expression for a temperature, which in particular, for the case of a Schwarzschild black hole, in 4 dimensions, then we know that for this we have f and g, they are 1 minus 2g m divided by r. Yeah, these are the functions for Schwarzschild. We know that the horizon radius is 2gm, so the Schwarzschild radius. So if you insert that into the formula, we get this temperature, which is 1 divided by 8 pi gm. So this is the Hawking result, the Hawking temperature. So this is the temperature for a Schwarzschild black hole in 4 dimensions. So this is equation 30. Yeah. So you see that here, as soon as quantum mechanics pops up into the game, as soon as we take quantum mechanics into account, then inevitably we are faced with thermodynamics, with temperature in this case. Yeah. So let's summarize what we have done. So we started with some curved background, which was very generic, just depending on some f, some g. I didn't specify at the beginning what f and g are. Then I assume that in this background I put some quantum field theory. So at the end of the day, you have a quantum field theory in curved spacetime. I assume that this theory is then in equilibrium will be in thermal equilibrium with the black hole. Yeah. Because I assume that the theory has a finite temperature. So I put some matter fields, for example. I put matter fields usually have a temperature, right? Because of the motion of atoms, molecules. So I put this theory at finite temperature there. So if I am able to find the temperature of the theory, then I also find the temperature of the black hole. So we were clever. We did this change of variables, which allows us to identify the metric in terms of the metric in polar form. So rho and phi were identified as polar coordinates. So phi is an angle with period 2 pi. So it means that tau is also periodic. And you know that the period must be equal to the inverse temperature. So we were able to fix the value of the temperature in this way. Yeah. So in particular, if we focus on d equals 4, so in 4 dimensions, and for a Schwarzschild where f and g are known, so they are this expression 1 minus 2gm divided by r, then it's easy to see that from the formula, then it's easy to get that. So this is the original formula which was proposed or found by Hawking in his paper. He used different methods for that, but we use this with this other way. We follow this other way to find that. Yeah. So this is the temperature of a Schwarzschild black hole. So you are not able to prove this, to derive this in general relativity, because in general relativity you have only a classical theory. Yeah. So we are able to derive this result as soon as you put somehow quantum mechanics into the game. Yeah. So this temperature is inversely proportional to the mass. So the larger the mass, the smaller is the temperature. Yeah, exactly. So this is the result that we wanted to get. And also, as a remark, it is clear from the previous computation that the existence of a horizon automatically implies a periodic time. Yeah, so we assume that there is an horizon, RH, and this automatically implies a periodic time. So a system with an event horizon is automatically also a thermal system. Yeah. So any system with an event horizon, like a black hole, then necessarily will have thermal properties like temperature. The other thing that I would like to show you is how to derive the entropy of the black hole, and then we are done for today. So the entropy is a little more, the calculation for the entropy is a little bit more delicate, but it's quite easy. So first, the starting point is to start from the partition function, which I have already written before, namely this one, the partition function for gravity. And in order to compute the entropy, we first approximate the partition function using the saddle point approximation. Saddle point approximation means that you can approximate the partition function in the following way. So you can write it as e to the minus s star, where s star is the classical action evaluated on the solutions of the classical equations of motion. On the solutions of the classical equation of motions. Yeah. So in other words, S star is the on-shell action. Yeah. So this would be our approximated value of the saddle point of the partition function. You see that there is no more integral there. Yeah. So this this saddle point approximation you do also in quantum mechanics, I think. So the idea is that you approximate, so you expand the action, you do a Taylor series of the action, and then at some point you will have a quadratic expression on the exponential. Then you can use the Gauss formula to integrate it out. So the integral disappears, and at the end you get just that. Yeah. So the action, the partition function is just the exponential to the power minus S star, where S star is the on-shell action. So the action evaluated on the solutions of the classical equations of motion. Now, the problem is that S star turns out to be divergent. Yeah, so it requires some regularization. And we regularize it by subtracting the action of some reference background. Yeah, so instead of computing S star of G, we compute the difference S star of G0, where G0 is some reference background. Now, the easiest reference background that you can choose is the Minkowski background, because it corresponds to the vacuum. So you have flat, nothing there. So we choose G0 to be Minkowski spacetime. Yeah, Minkowski can be considered as the vacuum solution because it's flat. And as soon as you go away from the flatness, then you have some higher order corrections. So let's subtract then S star G and then minus S star of G0, where G0 is the Minkowski. Yeah. So if you remember, S is the sum of Einstein plus the bulk term. The bulk term are the same. The bulk term vanishes. So we are only left with the boundary term. So this is just 8 pi G dm d minus 1x. So for of course I'm considering vacuum solutions for which R is 0. So that's the reason why I don't consider Einstein-Hilbert action. But I have to consider the other one, the Gibbons-Hawking term. Yeah, so with equation 31. So now let's evaluate this explicitly for a Schwarzschild solution, for a Schwarzschild black hole in d dimensions. Let's say d equal to 4, to be specific, d equals 4. Now we need the boundary of M. So let's suppose that let's suppose that our manifold is a ball, is a spherical shell. So we take the boundary to be a spherical shell at large radius. At the end, we will send the radius to infinity so that we can get the whole spacetime. Now, what is the boundary metric for that? Well, then gamma mu nu, it was the induced metric, so the metric on the boundary. Well, the first component is just 1 minus 2g and m divided by r, because we are in the Schwarzschild solution. Then we have the angular part, so the r squared and then r squared sine theta. And then then it's diagonal. So then it means that the square root of gamma is then equal to r squared sine of the square root of the determinant of gamma is r squared sine theta, then 1 minus 2gm divided by r to the power 1/2. Yeah. So now K has a property. The trace of the extrinsic curvature has a property, namely, when you multiply the square root of gamma times with K, this just gives you eta nu delta mu square root of gamma, where nu, as I said before, is the outward radial unit normal vector at the boundary. Yeah. So how do you express the unit normal vector? Well, if you were in flat spacetime, you would just write 1, 0, 0, 0, right? But here we are in the Schwarzschild metric, in the Schwarzschild background. So here we want to normalize with we have a new metric. So the unity of Minkowski, the normalization is not the same as in Minkowski. So it just have now these factors, so 1 minus 2g and m divided by r to the power 1/2. Yeah, so this is now the normalization of the unit vector for the Schwarzschild background. So if you now plug everything together, then we have d3x square root of gamma k.
Sorry for interruption.
Yes, okay.
Should the normal vector be like the minus half inverse.
Sorry?
So should the normal vector be 1 minus 2gm over r minus 1/2 power, not 1/2?
Why do you say minus 1/2?
Because if you contract with gamma mu u, then you can see that it should be minus 1/2.
Okay. Okay. Yeah. Probably. Yeah. But then. Yeah. At the end, the normalization must be respected. So yeah. Then probably there is. I forgot a -1 here. Yeah. Yeah. Probably I forgot the minus sign here. And anyway, the norm of that at the end must be 1. So so in order to do this, then if I have a minus sign here, then okay, yeah, then probably I forgot a minus sign. Then thank you for pointing this out.
And also in the last line, k by definition is the thing you wrote there, right? And if you want to multiply by another square root gamma, then you got to get an extra factor.
So you are talking about this?
Yes.
Yeah. So this is the property that we have of k that for k that one can show. So do you agree with this property?
Oh yes, sorry. Yeah, you are right.
Yeah. I mean, this is just a mathematical formula for just a property of k. I didn't show this, but this is true because I check it. So yeah, so this is just a property of k that we need. Exactly. So in order to compute this, I just use that property. So here I have an integral over x. An integral over x means an integral over theta, phi, and tau. So this is just an integral over theta, of the sine of theta. Then we have an integral over phi from 0 to 2 pi. And then we have the integral over tau. And I said that the time is periodic with period equal to the inverse temperature. So this is just an integral from 0 to 1 divided by t. And then we have the square root of gamma times k, which is exactly equal to also to this one. So if now you multiply, if now you multiply those, you should arrive to this expression. So this 2r minus 3gm. And then if you after that you integrate, you should arrive to minus 4 pi divided by t times 2r minus 3g m. Yeah, so this is the result for the first term. Then we have also the Minkowski contribution. Well, for the Minkowski contribution, the temperature is arbitrary. Minkowski is flat, so there is no way to fix a priori the temperature for Minkowski. But we fix it such that asymptotically the metric matches the Schwarzschild solution. So we fix the temperature for Minkowski such that, so in such a way that asymptotically the metric matches the Schwarzschild solution. So it means that we have to match the length of the circles of Euclidean time. So it means what does it mean? So it means that the integral over tau of gamma tau tau going from 1 to t, 1 divided by t, I require this to be equal to the integral over tau of square root of gamma 0 of tau tau of 1 divided by tau 0. So this length is the length of the circles. I require them to be the same. So on the left-hand side, I use gamma. On the right-hand side, I use gamma 0. Yeah, but they have to be the same. So if I now plug in into the integral, the expression of the tau tau component, then I arrive to the following equation or condition: 1 minus 2gm divided by r to the power 1/2 equal to 1 divided by t0. Yeah, so this we have a condition which tells us the relationship between tau and tau 0. Thus, for the Minkowski spacetime, we have root of gamma 0, then k0. We have 8 by t. If you do the calculation, you get 8 by t divided by r. So r is the radius of the spherical shell, times 1 minus 2gnm divided by r to the power 1/2. Yeah. So now we want to take the difference. Don't forget that we wanted the difference of that. And also, incidentally, you can see that from the previous one, you see that if r goes to infinity, then the integral is infinite. So that's the reason why I said before that the integral is divergent. And that's the reason why we need a regularization. So to something to absorb or to get rid or to cancel the r factor, which gives the divergence. So if we now take the limit for r going to infinity of the difference, then you can see that the r dependence cancel out, and this is beautiful because now the result is finite. So we are taking then the limit for r going to infinity. So we are extending the spherical shell to infinity. So we are covering the full space-time. This is the limit of the difference. So I have 4 pi divided by t, 2r minus 3gnm, then minus 8 pi divided by t, r, and then I have this square root, which I can Taylor expand. So I have 1 minus 1/2 2gnm divided by r plus the other terms and so on. Yeah. So now you can do it by yourself. You can just sum the terms, and then you see that the r terms with r cancel out. So you only have terms without r. In particular, you would find this. So 4 pi gm divided by the temperature T. Yeah. And now if you plug it everything in the action, so S of star of G minus S star of G0, then this is just the previous result with this additional factor in front. So minus 1 divided by 8 pi times minus 4 pi G m divided by T. Or you can write it as m divided by 2t. Yeah, because here the pi goes away, the g goes away, so you have m divided by 2 times the temperature. But now don't forget that the temperature, we found it to be 8 pi gm. So if you now use the previous result, then you can write this difference also in terms of beta. Also in terms only on t only and not on m. So express m in terms of the temperature. So get rid of m and write everything in terms of the temperature. So you get 1 divided by 2t times 8 pi gmt. Or this is also equal to beta square, where beta is 1 divided by t times divided by 16 pi gn. Yeah, so this the let's say the regularized entropy, which is the difference between two entropies actually. So the entropies that we wanted initially minus the entropy for the fixed reference background, so for Minkowski. Yeah, now that we have this, so this I should call it this big S, capital S, is the regularized entropy. And now that we have that, we can apply some usual thermodynamics relations that that you learn in thermodynamics. And for example, you can compute the free energy, the Helmholtz free energy. I think this is the correct name. So F is equal to minus the temperature times the logarithm of the partition function. So you have t, remember that the partition function was e to the minus the exponential itself to the minus s star. So here you have t times s star, well, actually the difference. So this means that this is beta divided by 16 pi g. And yeah, I also give us some number. This is my 33, 34. So this is the free energy. Then we can compute the total energy. According to thermodynamics, it's just the derivative with respect to beta of beta times f. So this is just beta divided by 8 pi gn, or also this is just m. Yeah. So here you are saying that the total energy of the black hole is just its mass. So the black hole does not rotate; it does have any charge. So the total energy just given by the mass. And last but not least, we have the desired, the thing that we most desired, namely the entropy. So the entropy is usually S, but I already used S for the action. So well, I just write entropy in words. So entropy is then equal to beta times the derivative with respect to beta minus 1 of beta f. So it's just the classical formula for the entropy from statistical mechanics from thermodynamics. So if you do this, you just get easily a beta squared divided by 16 pi g, or also you could express it in the following way. So A divided by 4g, where A is the area of the event horizon. So the area of the black hole, 4 pi RH squared. RH for a Schwarzschild black hole is just the Schwarzschild radius, so 2gnm squared. Yeah, so we recovered this very famous result, namely that the result of Bekenstein and Hawking, namely that the entropy does not scale with the volume of the black hole as one could think, but rather it depends on the surface of the black hole, so the surface of the event horizon. Yeah, and this idea was, Bekenstein had this idea, but he couldn't find the coefficient of proportionality. While on the other hand, Hawking was able to fix the coefficient of proportionality to 1 divided by 4g. Yeah. So we have seen in this lecture today how to derive some thermodynamics quantity for black holes, and you can do this only if you explicitly use quantum mechanics. So if you use GR, general relativity alone, then you are not able to derive that, because general relativity is just a classical theory. While on the other hand, as soon as you assume that you have some quantum theory or quantum field theory in a curved spacetime, then you are able to derive these results. And today we derive it with the path integral formulas. There are also other ways to derive that using these so-called Bogoliubov transformations. But I think the path integral formula is powerful because you don't because you just start with the expression of the path integral, and from there you do your calculations. Yeah. So as to conclude, so these results that we derive today, they still don't take into account quantum gravity. Yeah. So these are results which are derived using separately using a classical background, and then put in their quantum fields. Yeah, but this is still not a full theory of quantum gravity, because a full theory of quantum gravity has to treat both. It is a full theory where you have gravity and where gravity is full quantum, is a quantum object. Yeah. So if one is were able to have this theory, which we still don't know, then one expects this formula to receive corrections. So the entropy is not actually exactly equal to the area divided by 4G, but you receive some additional corrections if one has some a theory of quantum gravity. Yeah. So this Hawking result is just, if you want, the zero order term of a more general expansion. Yeah. So now the expression of these corrections are a bit long, but I can show you I can show you the expression of that from some paper. So I just go to my profile. So let's pick up this one. Okay, so in this paper, this publication of mine, I computed the quantum gravitational corrections to the entropy of a charged black hole. Yeah. So so the idea now, okay, now I just say it briefly because we don't have time, but the idea is to use this to compute the deviations from the Einstein equations by using this effective action which captures the effect of quantum gravity. So this is an effective action because it's a truncation. You can go to higher order. This holds for second order in the curvature. So you solve the new equation of motions, and then you find the modifications. So in particular, you first get the corrections to the metric itself. So you see the first contribution is the usual classical metric. And then you have some additional terms. So this should be interpreted as the effect of the quantum of the quantum gravity. So these are effects of quantum gravity effects. Yeah. And then if you can compute the entropy, and one can find the following. Yeah, exactly. So this using the so-called Wald formula, one find that the first term is A divided by 4G. So this equation 3.11. So you have A divided by 4G, which is the usual result, so n minus 2 pi q squared, because it's charged black hole. So this is the classical, this is the result of Hawking. But then you see that there are additional terms which are not predicted by original work of Hawking, but they are there as soon as you assume that that there is this effective action. So the entropy then is very long. So this is the expression of the entropy. So it's it contains some additional terms with some coefficients. Yeah, so this A area divided by 4G is just the first term of a more general expansion. Yeah, so you don't have to think that the entropy is just A divided by 4G. This is the first term. Then you will have some additional terms which captures the quantum gravity effects. Yeah, and of course one can, in principle, solve this order by order, computing the additional terms of the expansion of the entropy order by order. But of course, as soon as the order grows, then it becomes a little bit more complicated. Yeah, so if you are interested, then you can have when you have time, you can read my publication. If you want, you can also write an email to me. So maybe at the end, I just write my email in case someone wants to contact me. And I think we are done. So if you have some questions or some comments.